Hello, today in this video I would like to discuss the second mechanism of heat transfer, which is known as a convection heat transfer. In the previous video we had an idea about the first mechanism, which is called conduction heat transfer, and we said that the mechanisms of heat transfer, or the way that the heat transfer through a material is changing based on the phase of the material itself. So in case of a solid phase, the heat will transfer as a conduction, which we discussed it last video, and in case of liquid or gas, it will be by convection, which we'll discuss it today. Okay, this topic is a bit longer than the previous one, so I will do it on two separate videos, so you can understand everything easily and we can discuss everything in details. Okay, in this slide I will try to explain to you the easiest way how to drive the convection heat transfer module, or the convection heat transfer equation. Okay, as we mentioned earlier, that we want, or our objective, to find the Q, which is the heat transfer rate as a function of delta T, which is a temperature difference between the two materials or between the two surfaces, and we want to put here something called U, okay, in case of conduction, and we said U is called the U value of conduction heat transfer, and we said that this U is equal to the inverse of the thermal resistance, correct? Perfect. We will have the same scenario to drive the convection heat transfer model, or the convection heat transfer equation, but we will change this U value to something else called H, and we call it the heat transfer coefficient. From now on, you will see lots of textbooks or slide sheets or whatever, they saying the heat transfer coefficient, and we will discuss what is the heat transfer coefficient later on. Okay, so how to drive an equation expressing the convection heat transfer rate? If we imagine like there is a vertical wall, solid wall, and I have near to this wall a fluid, let's say air for example. Okay, this small layer near to the wall, it will be a bit stationary. Why is that? Because the viscosity between the wall and this layer is much higher than the other layers, which is in the direction of y, let's say, for example. Okay, so in here the velocity of the fluid, it will be 0. In here the velocity of the fluid, it will be higher than 0. Okay, so let's say we have an imaginary like layer of this fluid with a thickness x, and this layer we will assume that it is stationary, which is means there is no molecular movement, which is mean that heat transfer through this layer or between this layer and the vertical wall, it will be by conduction, because we said earlier the difference between the conduction and convection, or between the solid and liquid, the movement of the molecules of the material itself. If the molecule is stationary and there is no vibration, high vibration, it will be by conduction. In this case we assuming this. Okay, so in this case we can have the previous equation for the conduction heat transfer, and we'll put it in this way. We said that the Q over A, which is the heat flux, equal lambda, which is the thermal conductivity of this fluid, divided by x, which is the thickness of the layer, times delta T, which is T fluid minus T surface. In this case, we assume that the fluid has a higher temperature than the solid surface itself or the solid wall. Okay, like in real life, we can find this example like for example the external surface, external wall surface of houses, for example. In hot weather, you will find the air outside the house has a much higher temperature than the surface of the wall, so the heat will transfer from outside to inside the wall and then go to inside the house, correct? So it will be by conduction as we mentioned here. So Q over A, which is called heat flux, equal lambda, which is the thermal conductivity of this fluid, let's say air in our case, divided by X, which is the thickness of this layer, stationary layer, divided or times by the temperature difference between the fluid and the surface. Okay, here we can write this equation in this way, like we can say that the heat flux, which is Q per unit area, equal the heat transfer coefficient times the temperature difference. In this way, we can assume or we can understand that the heat transfer coefficient is equal to the thermal conductivity divided by X, which is the thickness of the layer or the thickness of the boundary layer, as we will see later. Okay, so the term heat, the term HC, which is the convection heat transfer coefficient, is ranging between different ranges. In case of liquid, you will find it between 1000 to 20,000. In case of gases, 25 to 250. That's why in case of liquid convection heat transfer, it will be much efficient than gas heat transfer or gas convection heat transfer. That's why if you want to cool something, let's say by water, it will be much efficient and faster than cool it by air, okay, because the heat transfer coefficient is much higher in liquid phase. Okay, we can calculate the imaginary thickness, which is X in here, okay, by knowing the heat transfer coefficient and the thermal conductivity. So we can find X is equal to, from here, yeah, X is equal to lambda divided by H. Okay, so this is the imaginary thickness of the stationary layer near to the wall in here, if you want to calculate it. Okay, we discussed this equation based on a uniform thickness of this fluid layer near to the wall, but in the reality or in real life, this layer, it will not be uniform as it is here. In real life, the layer near to the wall or near to the surface, it will take the shape as we see here in this diagram or in this plot. It will divide it to three different parts or three different areas. The first area it will call the laminar flow or the laminar zone, and then here it will be transition zone, and here it will be turbulent zone. Okay, you see here is that X, if we call it here, let's say X, it will be different from laminar to transition to turbulent. Okay, from now on we will put this X as lambda. Okay, we will call X as lambda from now on, and this lambda known as the thermal boundary or the boundary layer thickness which is thermal or velocity boundary layer, as we will say later. Okay, so here lambda or x is much less than here, much less than the turbulent. Okay, we called area, or we said area, that h is equal to lambda divided by x, correct? And here we said that we put x is equal to delta, which is the boundary layer thickness, so we can call h is equal to lambda, which is the thermal conductivity divided by delta, which is the thickness of the boundary layer. As long as this thickness increase, as long as the heat transfer coefficient decrease and the heat transfer rate, it will be less. It means in turbulent flow, the heat transfer rate or the heat transfer coefficient, it will be much less than the laminar one. Okay, great. Okay, if we have like here, like if we have a cross section in the turbulent or in the laminar or transition period, we will find that there is the velocity profile, it will be in this shape. This is our horizontal surface or horizontal sheet, and as we mentioned earlier, that the fluid near to the surface, it will have a velocity is equal to 0 because the viscosity is too high, and as long as I go far away from this surface, the velocity will increase. Okay, the velocity boundary layer or the velocity profile, it will be in this shape, and the boundary layer thickness, it will end up in the thickness of the boundary layer, the velocity boundary layer, it will end up when satisfying this condition that the u in this point is equal to 0.99 u infinity, and the u infinity is the free stream velocity of the fluid. Okay, great. The same scenario it will be for the thermal boundary layer. The thermal boundary layer, if we have here the surface, the horizontal surface, the fluid near to this surface, it will be in the highest temperature comparing to the far fluid layers, because this is the surface temperature, or let's say, for example, if we have a copper surface, and this copper surface is very hot, so all of the layer near to this surface, it will have temperature higher than the free stream one or free stream fluid, yeah. And the boundary layer thickness or the thermal boundary layer thickness, it will be end up when we achieving this condition, which is T at this point minus T infinity, which is the free stream temperature, is equal to 0.99 times T surface minus T infinity. So if I want to calculate the thickness of the thermal boundary layer, I have to find where is the point which is achieving this condition, and from this point to that point, it will be the thickness. Okay, the same scenario here, like when I found the velocity in here, which is 0.99 u infinity free stream velocity, so we find here the velocity boundary layer thickness. Both boundary layer, we call it as delta, but thermal, it will be thermal boundary layer. Okay, and the velocity boundary layer is called just delta. Okay, so we have two boundary layer thickness. Be sure or be aware that the thermal boundary layer thickness is not necessary to be the same or equal to the velocity boundary layer thickness. Great. So we have here the relation between the heat transfer coefficient and the boundary layer shape, as we saw earlier here, that the real boundary layer, it will be in that shape. So as long as the thickness of the boundary layer increase, the heat transfer coefficient decrease, as we say. Look here, because it's increasing, like in the beginning of this horizontal surface, it will be less. The thickness of the boundary layer, it will be much less than when we go in the direction of x, let's say, which is means the heat transfer coefficient decrease as long as we go away from the starting point or from the dead edge or the edge of the horizontal surface. Okay, great. After we understood this, now we want to speak about what is the forces which is affecting or working on the fluid layers in the case of the horizontal surface, as we discussed before. So if we imagine that the fluid is consisting of different layers, as we say here, and the fluid is moving in that direction because this is a free stream velocity, let's say u infinity, this is u infinity, okay, so in this direction, but at the same time there is a viscosity between these layers, between each other, and the first layer or the bottom layer and the horizontal surface. Okay, as long as the viscosity increase or the friction force increase, the velocity will be decreasing. That means the upper layer, it will be moving much faster or with a velocity faster than the lower layer. That's why we have this velocity profile, as we mentioned earlier. Okay, but remember, the velocity is a vector, which is mean a direction and quantity, but the thermal or the temperature is not a vector because it doesn't have a direction, or it doesn't like verifying by a direction as well. So when we write down or when we draw the thermal boundary layer or the thermal variation, you have to put an arrow like in here, but in case of the temperature you don't need to put an arrow, you just put like small lines or horizontal lines as I'm doing here. Yeah, okay. So here, as we mentioned before, like the lower layer, it will exposed to high viscosity and high frictional force, and the upper layer, it will be less viscosity or less friction force. That's why the velocity up there, it will be much higher than the velocity near to the surface. Okay. Shear stress is equal to the viscosity of the fluid times the velocity gradient in y direction. If we have here the horizontal surface, the velocity near to it is equal to 0, and the velocity here, it will be towards the free stream velocity. So the shear stress is equal to the viscosity times the velocity gradient, and the velocity gradient at y equal to 0 is the slope of the curve. Like in here, this is a relation between the velocity, which is u, and y, which is y direction away from the horizontal surface. So the velocity is increasing in the direction of y, and if we have the slope at y equal to 0, it will be the gradient of the velocity. Okay, shear stress is we deal with it like the same as the force, or we can say it is a static pressure. Okay, okay, great. Okay, what if I want to find out the shear force? we know that the pressure, generally the pressure is equal to force divided by the surface area or the acting area, correct? Sorry for my mess. Okay, so if we want to find the force or the shear force in this case, we can put instead of this pressure tau, which is the shear stress or static shear stress, equal force, which is a shear force, divided by area, which is the acting area. We call it here to just distinguish between it and the normal pressure area, like a small a. So if I multiply tau times a in here is equal to the shear force, which is equal mu a du by dy, because I have here the shear stress mu du by dy. So if I divide it, or if I'm multiplying times a, which is the surface area or the horizontal area of these layers, it will be the shear force. Okay, and as we said, this is the parallel to flow. Like for example, if I have the surface here like this in this case, and the flow in this direction, so this is A. Okay, be aware that all real fluids are viscous, and so the result in friction whenever the fluid flow. Like for example, in reality there is no flow without a viscosity. There is no flow with zero mu or zero viscosity. So any fluid moving over a horizontal plate, it will have a shear stress and shear force, and it will has a velocity profile, as we mentioned earlier. There is no fluid doesn't have any like, it's impossible to have a fluid without a velocity profile. Okay, so the first force which is acting on a fluid moving over a horizontal surface, it will be the viscosity or the viscous force. The second force is called an inertia force, and the inertia force is based on the velocity of the free stream. So in general, inertia is equal to mass times acceleration. If force is equal to mass, the mass times the acceleration, which is du by dt, because any acceleration is the changing in the velocity with respect of time, correct? So velocity or the velocity changing with time, which is acceleration, times the mass, is equal to the inertial force. If we have these two terms, m, which is the mass, and the time changing, we can call it m dot, which is the mass flow rate. Okay, so the mass flow rate times du, which is velocity change, this is the inertia force. Okay, remember that q, or let's call it v dot, which is the volume flow rate, is equal to, what is the relation between the volume flow rate with rho? Okay, so rho will equal to m over v, or equal to m dot over v dot, which is mean rho times v is equal m dot. So we can put instead of m dot, rho times v. Okay, and v dot, which is the volume flow rate according to the continuity equation, is equal to area, cross section area, times velocity. Okay, so we can put au, which is v dot from the continuity equation, we can au, and times rho, so we will have m dot, because m dot equal rho times v dot, and we can put V dot is equal to A times U. Okay, so the second force which is acting on the fluid moving horizontally over a horizontal plate is the inertia force. So we have a viscous force and we have an inertia force. Okay, is there any other forces? We'll see later on. Here, this is a real picture showing what is the difference between the turbulent and laminar. Laminar is to smooth flow, as we see here, and the turbulent is having lots of three-dimensional movement and it has lots of fluctuation, as we see here. Okay. Okay, in general, generally speaking, like in heat transfer and in thermofluid, when we discuss lots of topic, we have different units. Like for example, we can measure the mass is equal with a kilogram. We can measure the heat with watt and so on. So to write down a big equations or to make like a numerical model, it will be very complicated to deal with dimension parameters. To make it simple or to make life simple, so we started to find out a dimensionless group and we consider it one of the main parameters or one of the main properties of the fluid, and we can deal with it in a big or in a bigger situation or a bigger analysis. Yeah, for example, when you design a heat exchanger, it will be very difficult to calculate everything because you need to changing or you need to converting units from US to SI and so on. So engineers in real life dealing with dimensionless groups, as we will see later. The first property which we want to discuss is known as Reynolds number. What is the Reynolds number? In general, is a ratio or between the inertia and the viscous force, because we said earlier that we have an inertia force and we have a viscous force acting on the fluid. So if I divide the inertia force by the viscous force, we'll have something called Reynolds number. In case if the inertia force higher than the viscous force, which means the velocity of the fluid dominating the flow movement, and it has a quantity much higher than the viscous or the viscosity, so the Reynolds number will be high and the flow will be turbulent. Okay, in case the viscosity is dominating the flow stream movement, and the viscosity is much higher than the velocity or the acceleration or the inertia force, so the flow will be viscous and it will be laminar flow. Okay, if you try to imagine it, like if I have a flat plate and I have an oil moving over this plate, you will find the movement of the oil is much viscous than if we put water instead, or air, for example. In case of oil, we will find the flow is moving very slower than the water or than air. This means the viscosity or the viscous force is dominating the movement, and the inertia force have very less effect. Okay, in water or in air, you will find that the flow moving faster than the oil, which means the velocity or the inertia force is dominating the movement much more than the viscous force. Great, so Reynolds number can give us an idea if the flow is laminar or turbulent. In real life, if you want to find out if the flow is laminar or turbulent, you have to calculate the Reynolds number. What is the Reynolds number? Is the ratio between the inertia to the viscous force, and we can put it here from this equation. We said that the inertia force rho AU du divided by the viscosity force, which is mu, is the cross-section area divided by the velocity gradient in the y direction, as we said. So we can write down the Reynolds number rho u over mu, which is the viscosity, which is the density times the velocity, the free stream velocity divided by the viscosity, and we can remove this sign and put a constant instead times a dy divided by a. Okay, we can put instead of these two terms the constant, which we don't know, times a dy by a. We can put some characteristic dimension, okay, times this term rho u over mu, but this term which we are care about, okay, from different experiment, lots of experiment, we just accept that this dimension characteristic, it will be x. What is the x? The x is the distance from here toward the horizontal surface. So if we call it here, for example, this is the leading edge of the horizontal plate, and this is at the leading edge is the x equals 0, and as long as I go over the horizontal surface, the x will increase. Okay, so we said that the Reynolds number, okay, is a function of x, which is the leading, or which is the distance from the leading edge, and we put rho u over mu, which is the three parameters which like we are caring about in the equation. Here we call it Reynolds number with respect of x, which is mean local Reynolds number. If I calculate x in this point, I have Reynolds number completely different than x in here. Okay, why? Because when x is increasing, the Reynolds number increasing. If we go back in here, we'll understand this idea. Like in a small x, Reynolds number is small, which is mean laminar. But when the x is increasing, we will have turbulent, okay, which is a higher Reynolds number. Okay, great. Let's say, for example, flow tend to become turbulent when Reynolds number more than 500,000 over a smooth flat surface. So in case of flat surface, you will find the local x, if it's reaching a ratio or a quantity or a value more than 500,000, the flow tend to be turbulent. Okay, be aware that the geometry will have different Reynolds number or affecting on the Reynolds numbers. In the flat plate, horizontal flat plate, as we said, our turbulent Reynolds number is starting from 500,000. If we just doing it inside a tube or over a tube surface, it will be completely different measurement. Great. Here there is an example to practice this equation. We can say here airflow over a flat plate, the free stream velocity, which is u infinity, is 3.5 meter per second. At what distance from the leading edge is the flow expected to become turbulent? It takes the density of air 1.2 and the dynamic viscosity is 1.8510 with a -5 because it's air, so the viscosity is 2 little, you see. Okay, as we mentioned earlier, that over a flat horizontal plate, the flow starting to be turbulent when the local Reynolds number reach a value is equal to 500,000. So if we put this as our limit, 500,000, so we can have x, which is a distance from the leading point, by putting this equation over. So we have here 500,000 Reynolds times dynamic viscosity divided by rho u, which is the free stream velocity and the density. This is what happened here, and you'll find that the flow will start to be turbulent at a distance of 2.2 meter away from the leading edge. It's a very simple example to show you how to put the numbers in this equation. Okay, there is another example here. You can discuss it at home or you can do it at home. Great. Now we want to define another two properties of the fluid, which it will be very useful to use it in heat transfer analysis, in designing, for example, designing a process of heat exchanger or air handling unit or whatever. There is two diffusivity. There is two diffusivity, and it's different than each other. The thermal diffusivity and momentum diffusivity. Diffusivity word means the ability of something to diffuse or to penetrate this material. Let's say, for example, the momentum diffusivity is how easy the kinetic energy can diffuse through a fluid, or how easy the kinetic energy can go through a fluid, a bulk of fluid. Thermal diffusivity, it will be the same, how easy the thermal energy or the heat diffuse through a fluid. Okay, so the thermal energy, we give it alpha, and the momentum diffusivity, we give it nu, and momentum diffusivity equal the viscosity divided by the density, as we say here, and the thermal diffusivity is equal to the thermal conductivity divided by the density times Cp, and Cp is the specific heat at constant pressure, and we can take this value from our tables. It's like a property, like for example the enthalpy or the entropy. So you don't need to be worried about it. Like you go to the table at a certain pressure or certain saturation temperature, and you'll find Cp for each fluid. Okay, it's a property for the fluid, and at constant pressure it will be constant. There is another thing is called Cv, which is at constant specific volume. Okay, in case of latent heat there is no Cp or Cv, it will be equal C only, and this we'll discuss it later in case of boiling and condensation. So we have thermal diffusivity and momentum diffusivity, and this is the equation of using it. Okay, as we said before, that we want to create a dimensionless numbers or dimensionless groups to be easy to deal with. So the first group or the first number, which is the Reynolds number, describing if the flow is turbulent or laminar. The second number, it will be Prandtl number, which is the ratio between the momentum diffusivity divided by the thermal diffusivity, momentum to thermal diffusivity, and the Prandtl number is dimensionless number as well, and you will find it in a tables. So in case of high Prandtl number, the momentum diffusivity is much higher than the thermal diffusivity. That means the kinetic energy can penetrate or can diffuse through the fluid much easier than the thermal energy. Okay, Okay, now from different experiments, like in real life, we want to find, as we said before, that we want to find that the Q, which is the heat transfer rate by convection, is equal to H, which is the heat transfer coefficient, times delta T. Okay, and we can put here A. If you want to divide all of the equation divided by A, which is mean it will be the heat flux as we mentioned before. So Q over A equal H times delta T. We done all of this previous dimensionless group to find out H, which is the heat transfer coefficient, as a function of these groups, which is the Reynolds number and the Prandtl number. From lots of experiments, we have found out that the fluid or wide range of fluid follow, or the heat transfer coefficient of this fluid follow this equation. The local heat transfer coefficient is equal to constant times lambda divided by x, which is the leading edge distance, times Reynolds number with a power n, times Prandtl number with a power 0.33, and n and c, this is a constant based on the flow itself. So c and n are constants that depends upon whether the flow laminar or turbulent. Here it should be n, sorry, so you have to put it here n. This is a copy mistaken, yeah. So c and n is based on if the flow is laminar or turbulent. Okay, so this is the local heat transfer coefficient. If I calculate this one at a specific x, and I know Reynolds numbers from the previous equation, and I know the Prandtl number, so I can calculate easily the heat flux, which is Q over A, equal this heat transfer coefficient times the temperature difference between the surface or the flat plate surface and the flow or the fluid temperature. Okay, very good. Nusselt number, this is one other dimensionless number. This is equal to the heat transfer coefficient, which we are calculating from here, times x divided by lambda, and as we said, this x is the leading edge distance and lambda is the thermal conductivity. So we can find by experiments that this local Nusselt number is equal C times R e to the power n times Prandtl 0.33. How we get this? If you go in here, you will find lambda over x in here. You just put instead Nusselt number and you move lambda over x and you'll find this relation. Okay, in real life they can tell you, for example, in a designing a process, the Nusselt number of the process is equal, or the local Nusselt number of the fluid is equal to any number. And you can calculate the leading edge and you can calculate the thermal conductivity from tables, so you can find the heat transfer coefficient and you can calculate the heat flux or the convection heat transfer heat transfer rate. Yeah. Okay, so here's the flat plate as well, and this is X, this is L, and this heated plate with uniform surface temperature. We always assuming that the temperature is uniform, because if the temperature is different at different X, it will be very difficult to measure. Okay, so we assuming there is a uniform temperature over the plate. Okay, all of the previous explanation, it was based on a forced natural convection, which is the flow just move freely without any external force. Okay, in case of a forced convection over the flat plate, so the infinity or the u infinity or the free stream velocity, it will be much higher than the natural convection, which is like natural one. So it will be different relation of Nusselt, and like the constant will be different. You see here, when flow is laminar, which is less than 500,000, you will find the Nusselt number is 0.33 and Reynolds number with a power 0.5 and Prandtl 0.33, which is mean N and C has these values. And here, if it's turbulent, so the values of N and C will be different. Okay, so this is in case of forced convection. What about natural convection? What is the difference between natural and forced convection? Actually, it will not be too different, except that the velocity or the free stream velocity in case of forced convection will be much higher than the natural one. Okay, I hope this video it will give you an idea about convection heat transfer over a flat plate, and in the next video I will discuss the convection heat transfer in another geometry. As we said earlier, that the Reynolds number is changing based on the geometry itself. So if I have a turbulent flow over a flat plate, I have the Reynolds number is equal to 500,000. But if we have the same turbulent flow inside a tube, it will have a different number of Reynolds number. Okay, so in the next video I will discuss more about the convection heat transfer, and I wish everyone is okay, and see you later. Thank you very much. Thank you.